All right, so now we're going to switch gears and look at some different types of data that we really haven't experimented with in the lab before. So in this lab, we're going to work with thermal data, and then in the following lab, we're going to play around with synthetic aperture radar data. Okay, so the data you're going to use for this assignment is from the Landsat 8 platform. You're going to use data from OLI, or the Operational Land Imager, which has collects the visible near-infrared and shortwave infrared data, and then you're going to use the band 10 from the TIRS sensor, which is the thermal data. So this is the optical or multispectral data shown here with the false color composite, where red shows shortwave, green shows near-infrared, and blue shows green. And then this is the associated temperature data, just with a red ramp on it. And this is, as you see, a little coarser because those bands are collected at coarser resolution. And you don't really need this, but we also provided an LCD because just as a reference. Okay, so effectively what you're going to do in this lab is step through the process of converting these calibrated DN values from band 10, which is again from its thermal data, into an estimate of surface temperature. And that's just done with a series of equations, and you can do basically most of this with just like processes and raster calculator. Note that we also provided the metadata if you need to look up specific values. Okay, so again, some general questions about thermal data, and then again we gave you the metadata to pull out some of the needed coefficients and whatnot, and then you're going to step through this process. So the first thing to do is convert from the calibrated DN into radiance using the appropriate multiplication addition factors there, and that's going to produce the top of atmosphere radiance estimate. To actually estimate temperature from that, you'll apply this equation, and then we're going to convert it into Celsius by just subtracting the 273.15. So that's going to give you top of atmosphere brightness temperature, which is, again, different from surface temperature. So to estimate surface temperature, we need to integrate in emissivity and then also wavelength. So first thing is to estimate. There's different ways to estimate emissivity. What we're going to use is this NDVI method. So you can calculate NDVI. Again, you can do that with raster calculator, or you could do it with like the index tool, the NDVI index tool, or even with like one of the raster functions. And then once that's created, you're going to create this proportional value object, which is an estimate of the percentage of vegetation, which is correlated with emissivity. By taking the NDVI value at a cell, adding the minimum in the grid, NDVI value in the grid, and then dividing by max plus min. To get the min and max, whenever you make the NDVI, you can just grab the high and low values in the stretch. So this is showing that output there with raster calculator. And then next you're going to try to estimate emissivity from that. So you effectively take that proportional value, multiply it by this term, and then I think that's actually back. That should be add. I think that's wrong. Anyway, I'll fix that beforehand. But you'll use this equation, and then lastly, to convert to surface temperature, you're going to use your top of atmosphere brightness, and you're going to and then apply this correction, which takes into account the emissivity, and then lastly convert to Fahrenheit. And you're going to deliver a map layout with two images. One is the false color composite. The other one is the temperature estimate in Fahrenheit. So again, a lot of this is done using raster math, raster calculations. So you're just effectively manipulating this into different units that approximate surface temperature, as opposed to just these calibrated DN values.